Hey everybody, Dr. Retzek here with you. This is our first video in 14.7, which is about optimization. Let's get started. Okay, so the name of the game here in 14.7 is you're trying to find maxes and mins, and it goes a lot like it used to go in Calc 1, except now the pictures look something like this. You got our flying carpet, only it's got some dips and swales and mounds in it, but this is still, say, z equals f of x, y. And we're trying to find the spots that are good candidates for maxes and mins. And the good candidates, as we've been discussing, are spots where the tangent plane is horizontal. And spots where the tangent plane is horizontal correspond to spots where the gradient is the zero vector, because if the tangent plane is flat, then that means it's flat in the pure x direction and it's flat in the pure y direction. In other words, df dx and df dy are both zero. Okay, so to find critical points, we're going to look for spots where the gradient is either zero or fails to exist. Failing to exist, that would be spots maybe where you had a sharp corner, like at the top of a witch's hat. But these are really our prime candidates for locating maxes and mins. The purpose of today's video is to carefully do a single example. Okay, so rather than looking at that specific or unspecific, I should say, surface above, let's get an actual function into the mix here. So let's find critical points, CPs for short, for the function f of xy equals x cubed plus 3xy squared minus 15x plus y cubed minus 15y. All right, so this is a reasonable function of two variables. It's a polynomial in the sense that it's just some linear combination of powers of x and y. You can see if you take partial derivatives with respect to x and with respect to y, those partials exist everywhere. We have no issues here with, I don't know, division by zero in a denominator or square roots of negatives. None of that is happening here. By the same token, no one can just look at that and think, oh yeah, I can totally picture that surface. This is a fairly complicated object, and it's not something that we could visualize without further analysis. Okay, so let's find those critical points. Remember, critical points are spots where both partials are zero or at least one partial fails to exist. On this problem, the partials exist everywhere, so we're looking for spots where the partials are zero. So we're trying to find x comma y such that df dx comes out zero and df dy also comes out zero. So let's compute those partials and see if we can figure out where they are simultaneously zero. Okay, here we go. All right, partial with respect to x. We're good at this point in chapter 14. So what do we got? 3x squared plus 3y squared minus 15. And then partial with respect to y, 6xy plus 3y squared minus 15. Okay, so there they are. Those are the partials with respect to x and y, respectively. We are interested in where they come out zero. So look at those two expressions for partial with respect to x and partial with respect to y. Let's focus on the partial with respect to x for a moment. We see partial with respect to x comes out 0. That happens precisely if x squared plus y squared equals 5. So the x comma y's, where the x partial of our function comes out to 0, are actually a circle. So I want to draw that circle in the xy plane. So here's the circle. Its radius is root 5, and it's centered at the origin. So in the xy plane, that entire red circle is where the x partial comes out to 0. So at any spot x comma y on that circle, the x partial is 0. But remember, we're looking for spots x comma y where both partials are 0. So now we have to ask ourselves, for the points x, y on that circle, which locations also make df dy come out to 0? So what points on this circle also make df dy come out to 0? Okay, so consult your expression for df dy at the top of the page there. Let's see. If you're talking about a point that's on that red circle, then x squared plus y squared is 5, or in other words, y squared is 5 minus x squared. So at this point right here, for sure, y squared is 5 minus x squared at that point, at any point on that circle. We're going to look back at our expression for df dy and substitute y squared equals 5 minus x squared. So 6xy plus 3y squared comes out to 15, precisely if 6xy plus 3 times, okay, y squared is 5 minus x squared at any point on that circle. And that happens precisely if, let's see, the 15s cancel, so I think we got 6xy take away 3x squared comes out to 0. And then we can factor out 3x. And so then we get 2y minus x comes out to 0. So what that's telling us is, of all the points on that red circle that make the x partial come out to 0, only certain ones of them make the y partial also come out to 0. Focus on this piece. Certainly if x is equal to 0, this equation is true, and the y partial is also 0. So therefore, specifically here and here at 0, negative root 5, and 0, root 5, those are two spots where the partials are both 0. But it's not the only two spots. There's also this possibility. Any spot where the x is equal to twice the y is also a spot where the partials both come out to 0. And on that circle, if x is twice the y, then this circle is 2y squared plus y squared equals 5. So 5y squared equals 5. So y equals plus or minus 1. So this piece yields y equals plus or minus 1, and then x equals twice that. X equals plus or minus 2, where the plus goes with the plus and the minus goes with the minus. And this spot yields x equals 0, y equals root 5, and x equals 0, y equals minus root 5. So we found 4 spots on that circle where both partials are 0. Let's mark those 4 spots. We've already marked 2 of them, so we also have 2 over 1 up, maybe right about here. And we also have negative 2 over 1 down, maybe right about here. So there's 4 spots. And those are the only critical points. Those are literally the only spots in the xy plane where both partials come out to 0. 4 points. Okay. As you can see, finding the critical points for a function can be algebraically intensive, and there's no recipe. So from problem to problem, you're just going to set both partials equal to 0, and then it is an utter free-for-all. One way or another, by hook or by crook, you have to find all the x comma y's that make the partials come out 0. So get creative and dust off your algebra skills. That's how you find those critical points. Now, let's talk about what to do with the critical points. So now you've got this long list of critical points. You still don't know whether those critical points correspond to maxes, mins, or maybe neither. For example, you could have something like this, where indeed the spot you found where the gradient is 0 corresponds to a max. Or you could have this, where there's a big valley, and the spot you found corresponds to a min. Or perhaps, most frustratingly, you could have found this. Remember the saddle. You might have found this spot. Where the tangent plane is neither always below or always above near that location, but sometimes below and sometimes above the surface. So it's sort of concave up in one direction and concave down in the other. Those are called saddle points. And the good news is we have a tool called the second derivatives test that can help us decide whether each of the critical points we found is a local max, local min, or saddle. Here's the tool. This is how you check. To decide local max, local min, or saddle. Here's what you do. You compute second x partial times second y partial. Take away square of mixed partial at each critical point. Let's give this quantity a name. This is called the discriminant, sometimes called the Hessian. I'm going to call it capital D for the purposes of this discussion. Possibility 1. If D is positive and second xx partial is also positive, then you have a local min. Possibility 2. If the discriminant is positive and fxx is negative, you have a local max. Third possibility. If the discriminant is less than 0, you have a saddle point. Last, worst possibility. Well, what possibility about big D is unaccounted for at this moment? You got it. If big D is 0, no info. And you have to do something else. Your problem is harder in that case. It's just not clear. You have a couple suggested problems where you get to consider that possibility as well. I will leave it for you guys to test these 4 critical points that we found in this example. For local max, local min, saddle, or no info, according to this theorem. This theorem, this is called the second derivatives test. So this is a theorem specifically for functions of 2 variables, and it helps you some of the time, as long as you're not in case 4 there, classify the behavior of the surface at the critical points you found. All right, and that's what most of your suggested problems are on here in the first part of section 14.7. Our second video will sort of rein things in a little bit, and we'll be thinking about surfaces with domains that are closed and bounded, flat in the xy plane, in which case, a lot of the time, we will rightly expect absolute maxes and absolute mins. So that's coming up tomorrow. Anyway, go practice some of this early 14.7 stuff. It's all about finding critical points and testing them with second derivatives test. All right, keep up the hard work. We are almost done with chapter 14, and I'll see you next time. Bye.